Hey everybody, this is Mr. Bortnick. I'm back trying to work on our Unit 8 videos. I know it's been a couple of years and I've seen the comments that have been being left on my Chapter 7 videos. And so I'm trying to finish off that AP Calculus curriculum. With that said, we're jumping today into Unit 8, which is Applications of Integration. And we're going to be talking about topic 8.1, which is finding the average value of a function over an interval. Enjoy today's notes. All right, welcome to Chapter 8, Applications of Integration. We're going to start today with 8.1, Average Value of a Function. We're going to start by recalling a little bit as we're beginning this new chapter, specifically of some things from earlier in the year. We're going to start with this intermediate value theorem, which, if you're thinking about reviewing as we get closer to the AP exam, this is coming from back in section 1.16. And in general, if we think about the intermediate value theorem, we know that it allows us to guarantee a function hits every output between two given outputs if the function is continuous. And this is really big as we think about back in chapter 1. One of the big things for us to know that's going to hit every output between those two given outputs is that this function is continuous, that there's no skips, there's no jumps, there's no steps. It's going to hit every single output or y value as it goes from the two outputs that we were given for this function. Additionally, there was we've hit many times this year average rate of change, which we know just generally from like Algebra 1 class, even back then, that this is our slope formula. Thinking about the slope between 2 points. And we know that this version of it, this f of b minus f of a divided by b minus a, is essentially our calculus version of doing y2 minus y1 over x2 minus x1, where we're finding the coordinates between 2 points x1 comma y1 and x2 comma y2 using our slope formula for this. This then led us into the mean value theorem, which if we're thinking back, this is something that we covered back in chapter 5 for this. And this said that f prime of c is equal to f of b minus f of a divided by b minus a. Specifically, that our instantaneous rate of change needs to be equal to the average rate of change if a function is continuous and differentiable on a given interval for this. And so I'll just highlight that this is our instantaneous rate of change. I'm going to say IROC. And our slope here is that average rate of change like we've got listed above. And one of, again, the key things that we need to know for this to be true, unlike in chapter 1 when we were talking about intermediate value theorem where a function needed to be continuous, the mean value theorem has two requirements, specifically that the function is both continuous and differentiable. All right, so this is going to lead us into a new formula for today, which one thing to just mention, the title for today's lesson is average value of function. That's what we're going to be finding here in our equation that we've got here. This is worth mentioning just because sometimes it can be confusing when we're talking about average rate of change or mean, right? Some frequently, like if we're thinking about the mean of a set, we might be referring to the average of the set. There are a lot of averages that are coming up in AP Calculus, and so it's important to think about the context that we've got. Specifically, if we're thinking about the average value of a function, we're thinking really about the average height of a function for that. So I'll highlight that here on the side, that when we're talking about that average value, specifically what we're trying to find is the average height over an interval. And the formula for this is going to use integration as we've been doing over the last couple of chapters. It's going to be 1 over b minus a times the integral from a to b of f of x dx. And specifically, this is going to give us the average value of a function on the interval from a to b. And so specifically, most of the time when we're talking about these, depending upon the inputs, we're thinking about the x values of the interval for this, going from an x value of a to an x value of b. This is essentially finding the area between the curve and the x-axis from a to b, and then we're dividing by the width of the interval going from b to a, or from a to b in this case. And so this is going to together find us the average height over that interval. Let's see a couple of examples here as we jump down here to problem number 1. We're going to be using specifically our technology for today to find these integrals. Remember, back in chapter 6 and chapter 7, we learned how to find integrals by hand using antiderivatives. Today we're going to take advantage of our technology in order to solve many of these integrals that are here. So if we want to find the average value of f of x, which is the equation 6 minus x squared on the interval from -1 to 3, really we're thinking about x values going from -1 to 3, and that is going to be my a and my b for my problem here. If we plug into our formula, which is specifically that average value from up here, this is going to end up being 1 divided by our b value, which is 3, minus our a value, which is -1, times the integral from -1 to 3 of our f of x function, which is that 6 minus x squared with respect to x, so dx here at the end. Now, if I'm trying to evaluate this, I notice that there's two things. There's our integral, and there's this essentially fraction in the front. I'm going to start with the fraction bit. If we do that 1 divided by 3 minus -1, that minus is going to cancel out, meaning that's going to be the same thing as 1 over 3 plus 1, or 1/4 here in the front. And then this integral, as we said, we're going to use some technology here. We could evaluate this by hand using antiderivatives, but I'm going to use my graphing calculator here, like we talked about back in chapter 6, to find this antiderivative. If you evaluate that, this is going to end up being about 14.667 if we're rounding to 3 digits after the decimal place. And together, if we do 1/4 times that 14.667, this is going to give us an answer that's about 3.667 when we round to 3 digits after the decimal place. But that would be our average value. And if we're thinking about what this is telling us, I'll just take a look at the image over here. We do have a picture here of that 6 minus x squared, that parabola shape that's opening downwards because of that negative sign, and it's been shifted up 6 units, so we see that the vertex is up at a height of 6. If we found the integral from -1 to 3 of this function, we know that that integral is going to find the area between the curve and the x-axis. And so here is x equals -1, here is x equals 3. And so that integral is finding the area between that curve and that x-axis, essentially of these two parts that we've got here, here in red. Between that curve and that x-axis, both are positive and are negative for that. Now, by finding the average value of this, and by saying that this is 3.667, essentially I'm saying that this is the average height of the function. And so if I take a look and I draw out about 3.667 on that interval, I am essentially saying that the height here, I guess two things. The average height is this 3.667 from -1 to 3, which, sort of makes sense because we've got some negative area, we've got some positive area that would cancel out with what we've got here. But additionally, essentially this blue rectangle that I've drawn has the same area as all of this red area under the curve when we take into account that positive and that negative area here for this. The second part of this question, though, is asking us, when does the function assume this value? That's going to be when the actual output of the function equals this 3.667. So in order to solve for that, we're going to actually set our f of x, that's 6 minus x squared, equal to that 3.667. And we're going to solve using algebra in this case. So realistically here, we would want to subtract 6 from each side of our equation. That would give me that negative x squared is equal to 3.667 minus 6, which would give me about negative 2.333, repeating in this case. And then we could divide each side by that negative sign, giving me that x squared is going to equal positive 2.333, repeating. And then to cancel out that squared, we can take the square root of each side, meaning that x is going to be equal to the square root of 2.333, which would be about 1.527. And so that would be the value, or when the function assumes that value of that height of 3.667. And I can sort of visualize that this looks like it's about 1.5. If I go over it here when x is equal to about 1.5, that does look like where it's hitting that height of 3.667, like we said before. So our answer can be justified and hopefully reinforced by the picture that we're seeing here as well. Let's take a look here at our next question. We've got two left. Taking a look at problem number 2. We want to compare our average rate of change and average value of a function. Again, the fact that these both use the word average, from looking at average rate of change and average value, it can be confusing. But we want to remember that average rate of change is the slope of the function, while the average value is this essentially average height over the interval. For problem number 2, they give us h of t is equal to negative 16t squared plus 41t plus 10. H is in height in feet, and t is time in seconds. What is the average height during the first 3 seconds? Here specifically, because they told me that we're talking about the average height, we want to be thinking about our average value. And so specifically, since they're talking about height, I'm using that average value equation, which was the one that we introduced today in our up here in this box, thinking about that 1 over b minus a times the integral from a to b of f of x dx. So if it's over the first 3 seconds, specifically here, I'm thinking about from the t values t equals 0 to t equals 3. That would be over the first 3 seconds for that. So plugging in, realistically, my a is going to be 0, my b is going to be 3 for that formula that we were talking about up at the top. That looks like that this is going to be 1 divided by 3 minus 0 times the integral from 0 to 3 of our h of t equation, which I'll put our negative 16t squared plus the 41t plus the 10 with respect to our time. And if we're taking a look at that integral, again, we're going to continue to use our technology here to evaluate this. Essentially, I can throw this all into my calculator using our fn int feature to do the 1 over 3 times this integral. If we do that, this is going to end up equaling about, this looks like 23.5 feet for that. So, and again, that is from using that equation and plugging into the fn int feature on our calculator to evaluate that integral for us. And again, this is one we could do by hand, right? We know how to do antiderivatives from our work in chapter 6, but again, the goal for today is just using this average value equation. What about b? What is the average velocity during the first 3 seconds? Well, they use this word average, and again, I need to be thinking about which equation they're talking about. Since the original function was in terms of height, right, that is a position, I know that velocity is the derivative of position. And so I know that in order to get that velocity, I'm going to need to be thinking about the derivative or the slope. And so because of that, this is making me think more of an average rate of change, while in our last problem, we were using that average value equation for this. If I'm going to be doing my average rate of change, I'm still using, since it's the first 3 seconds, I'm going to be still using the same t values from 0 to 3, but my equation is going to be different. I'm going to be using this equation here, my f of b minus f of a over b minus a. And so for that, this, at least in terms of the function that we've got here, since it's h, this is going to be our h of 3 minus our h of 0, divided by 3 minus 0 for that. And essentially what I would need to do if I was going to evaluate this is I would need to plug 3 in into my original h function to figure out the height when t equals 3, and then I would need to subtract the height when t equals 0 by plugging that 0 in for this. In general, again, evaluating this and then dividing by that 3 minus 0, we are going to get an answer in this one, which is negative 7 feet per second, and that is because the heights here were in terms of feet. The time we're dividing by is in seconds, so we end up with units that are feet per second for this problem. Again, I'm leaning heavily here on calculator usage in order to evaluate these. Just really the goal for today is trying to think about that we're using the right equation in the right problem. Let's take a look at problem number 3. R of x is equal to 2 sine of x minus 1, where r is the rate at which Mr. Brust's waistline is changing in inches per month, and x is the time in months. One thing that I'll notice, two things here, just thinking about some work we've been doing since earlier in the year. Notice here that they gave us a rate, and the waistline is in inches per month. And so this is sort of telling me that we're already dealing with something that is essentially a derivative, because it is a rate, and we see the units are also a rate in inches per month. And our question here is, in part A, is asking us what's the average rate of change? So the average rate of change that Mr. Brust's waistline changes from the 10th month to the 12th month. Since the original function is already a rate, even though this is using the phrasing of average rate of change, which makes me think of a slope, we're going to need to be using essentially the average value equation here. So I'm going to highlight the average value equation, even though they use the phrasing of average rate of change here, because we already have a rate. I don't want to take a derivative again or think of the slope of this function, because then I would have the rate of the rate. And so we want simply the average value for this, which would be the rate of change for that. So in this case, we're going from our t equals 10 to t equals 12. That is going to essentially be the a and the b in my average value equation. This looks like this is going to end up being 1 divided by 12 minus 10 times the integral from 10 to 12 of our r of x equation, so that 2 sine of x minus 1 with respect to x, so that dx here. From plugging that in and using our technology here, that fnint feature, this looks like this is going to end up being an average height or average value of negative 2.683 inches per minute. And so this is going to be, looks like the average amount that this waistline is changing per month between the 10th and the 12th month for that. So, and that's not inches per minute, but looks like inches per month for that. Excellent. Last one here that we've got what is the average change of this rate during the first 5 months. And so if we're talking about how the rate itself is changing, this is where we're going into essentially our average rate of change equation for this. And so again, I'll just highlight sometimes the toughest part of these is trying to figure out, based on the wording in the problem, which equation to use based on what they gave us. And so paying attention and being really deliberate is really important here as you're working through, so that you're not mixing up these two equations for this. What is the average change of this rate during the first 5 months? Well, we're using that average rate of change. So if it's during the first 5 months, we're going to be going from t equals 0 to t equals 5 for that first 5 months. And then plugging into that average rate of change formula, we're going to need to do r of 5 minus r of 0 divided by that 5 minus 0. Again, in order to evaluate this, I'd be plugging 5 into my r of x equation, and then 0 in as the input for my r of x equation, subtracting those two values, and then dividing by that 5 minus 0. Through our calculator work, though, this is going to end up being negative 0.384. And since the rates themselves were already in inches per month, when we divide by those months again, this is going to end up giving us units of inches per month squared for that. And so highlighting that, that is going to be our final answer for problem number 3. As usual for these, we know that we get better from doing practice, and so I encourage you to make sure that you are looking at the practice problems. We've got a bunch here to be taking a look at to help us prepare for any upcoming quizzes and tests. But otherwise, thank you so much. I hope you have a great rest of your day.